And now here's where the real fun begins. So how many of you guys want to admit to being a little bit confused on the whole like pKa, which form predominates, pIs, all that lovely stuff? Sweet. In about 15 minutes, you will no longer be so. It's going to be fabulous. So if you look, going back here, to your Henderson-Hasselbalch. So earlier we talked about how this ratio can affect the pH of a buffer, let's say. So when this ratio is exactly 1:1, what was the pH of that particular buffer solution? It was equal to the pKa value. Now, if you had more base than acid, then what would happen to the pH of that solution? It would be more basic than the pKa. Well, if you had more acid than conjugate base, then what would be true about the pH of that solution? It'd be more acidic, lower than the pKa. So cool. So we talked about how this ratio could affect the pH. Now we're going to do it in reverse. It works exactly the same way. We're going to talk about how the pH affects the ratio instead. So here's the deal. If the pH is lower than the pKa, i.e. pH is more acidic than the pKa, well, if it's more acidic than the pKa, then which one of these must be predominating in the solution? The acid form. And so in this case, that would mean the concentration of HA is greater than the concentration of A-. And technically, every pH unit you're lower than the pKa would be 10 times more of the acid present. So if you were 2 pH units lower than the pKa, you'd be 100 times more in the acid form than in the base form. Works the other way around as well. If the pH is a more basic number than the pKa, then you're going to have more base. In this case, A- would be greater than the concentration of HA. And every pH unit, again, would be a power of 10. One pH unit higher than pKa value for the pH, 10 times more conjugate base, so on and so forth. That's how this works. So let's look at this for a minute. Let's get your typical amino acid on the board. So, and let's put it entirely in the acid form. And let's say it's one of the amino acids where the R group does not have a pKa, is not acidic or basic to any degree. So the only acid groups we have are the N-terminus and the carboxy terminus. So in this case, the N-terminus, what was his pKa generally? About 9 to 10. Oh, well, sweet. What this means is that if your pH is around 9 to 10, you'd have equal amounts in the conjugate acid form and equal amounts in the conjugate base form. But notice, what if your pH was much more acidic than 9 or 10? Which form would predominate? Acid form. Much more acidic than the pKa, acid form predominates. Makes it easy to remember. What if the pH was much more basic, way higher than 9 to 10? Then the base form would predominate. That's how it works. So for this group right here, what would the base form of him look like? We'll draw the rest of the carboxyl group here in a little bit, but the base form of the amino group would look like that. There's the acid form, there's the base form. What's the charge on the acid form? +1. What's the charge on the base form? Neutral. Sweet. So notice, if the pH is lower than 9 or 10, acid form predominates. If the pH is higher than 9 or 10, base form predominates. If the pH is close to the pKa value, you'll have a fair amount of both in your solution. Cool, that's how it works. It's really as simple as that. Now, once we put 3 pKa's in the same molecule, it gets more confusing. But in principle, you can examine them one at a time, and it is as simple as that. So let's look at the carboxylic acid group here. What's the pKa of a carboxylic acid group? About 2. About 2. And so if the pH was exactly 2 in my solution, then what would be true about this carboxyl group? Half of it would be in this conjugate acid form, and half would be in the conjugate base form. So I'm going to draw that conjugate base form. For carboxylic acid, the conjugate base is a carboxylate. Cool, so now here's a source of confusion. What's the charge on the acid form of a carboxylic acid? There isn't one. But what's the charge on the conjugate base? -1. So notice for the amine, it was plus versus neutral. But for the carboxylic acid, it's neutral versus negative. And so we got a different kind of charge pattern, at least what I'm going to call a charge pattern, for amines and carboxylic acids. Notice, as you go from acid to base form, you get one less plus charge, because you're losing an H plus, if you will. In either case, one less plus charge, one less plus charge. So that's still consistent with everything we know about Bronsted-Lowry acid-base stuff, right? So, but the actual charges themselves are indeed different between the two. And that's going to be important when we start using, at a certain pH, given all these pKas, what would be the charge on this peptide? That could be fun. All right, so let's look at this. So pH 2, I'd have equal amounts of molecules in the two different forms, acid, base. What would the pH have to be if I want this form to predominate? Lower than 2, more acidic than 2. What would the pH have to be if I want this form to be the predominant form of solution? Higher than 2, more basic than 2. That's the way it works. So now let's talk about pH 7 for a minute. Physiological pH, right around 7, well, 7.4 or whatever. So for the amine group, actually let's go with the carboxyl group. We were just talking about it. For the carboxyl group, which form will predominate at pH 7? Well, at pH 7, we're more basic than that number, and so the base form is going to predominate. Which form would predominate at pH 7 for the amine group? Well, pH 7, we're more acidic than that number, and the acid form would predominate. And so notice neither one of these molecules is the predominant form at pH 7. At pH 7, we said the carboxyl group would be predominantly in the base form, but the amino group would predominantly be in the acid form. And so for a typical nonpolar or at least non-charged R group amino acid, what would the charge of the entire amino acid be at pH 7? Neutral. It has a plus charge and a negative charge, but overall it's neutral. What's the special name we give to this thing? Yeah. There's your Z word of the week. Zwitter ion. That's a word worth knowing. It's a doubly charged, but overall neutral amino acid here. And it's the principal form of all the nonpolar, or at least neutral, R group amino acids at pH 7. We can also talk about what's called a pI. pI, the isoelectric point. The isoelectric point is where the average charge of the amino acid in solution is indeed 0. Notice we said, in this case, we said that, at pH 7, this is the predominant form, which has a charge of 0. But if this is the predominant form, is it the only form present in solution? No, in solution, you're still going to get a few molecules that look like this. You're still going to get a few molecules that look like this and stuff like that. But this is just the predominant form. Well, we want to find out when the exact average form comes out to having no overall charge. And if all you got is 2 pKas for an amino acid because the R group doesn't have a pK, you just take the average of those 2 pKas and you're done. And so in this case, the average of 2, in this case, you'd probably be given a value of 2 point whatever for whatever amino acid. You give an exact value. And you get the amino group's exact value, and you just take the average of the 2. That would be the pI. That would be the pH where that particular amino acid would have an average charge of 0. Cool. And that has implications for when we do like electrophoresis and stuff like that, but we won't go there. So, all right, so let's make this a little more complex. Let's say we got something like lysine. What class or what category of amino acid was lysine? Basic amino acid. It's one of the basic amino acids. And it was also one of those amino acids that at pH 7 had what kind of charge on its R group? Positive charge. Sweet. We'll see why that is here. So let's look at lysine here. And you know what? Let's start in the most acidic form of lysine. This is the most acidic form of lysine. But we're going to get more specific than just R here. Lysine has an R group. And being a basic R group, what do you suppose is the main functional group down here? It's an amine. It's an amine. And I don't care if you know what the amine looks like. You could just write, something generic here, but technically it's a 4-carbon chain, 1, 2, 3, 4, and then the amine. And I'm going to again draw all groups in their acidic forms. All groups in their acidic forms. Cool, so there's lysine. So the amino terminus, the alpha amino terminus here, the N terminus, pKa should be again approximately 9 to 10. The carboxy terminus should be approximately 2. But this guy right here is not one you have to memorize. The R group actually has a pKa. And so if we look on our chart there, for lysine, pKa is 10.53. How low would the pH have to be for this all-acid form to predominate? Lower than 2. Lower than 2. If I'm lower than 2, then I'll be lower than everybody's pKa, i.e. more acidic than everybody's pKa, and the acid forms would predominate. So this is the form that would exist for a pH lower than 2, predominant form for pH less than 2. So I started out at pH 0, let's say, and I just incrementally started adding to a big solution, drop by drop, of sodium hydroxide, just very gradually bringing the pH of the solution up. Okay. At what point, as the pH starts at 0, at what point as it rises is the predominant form going to first change? 2. Once I cross 2, he switches. And so the next form we'd see I'm going to draw that R group really tiny from here on out, save a little space. So in this case, this pH would correspond to greater than 2. But to stay in this form, it has to be greater than 2, but not greater than what? Can't be greater than 9 to 10, because that's when he starts to change. So in this case, really this would be a range of like 2 to 9 maybe. Somewhere in that range. It's going to be predominantly in this form right here, including, notice, what remarkable pH is included in that range? 7. And so what would the overall charge of the predominant form of lysine be at pH 7? +1. Notice, that's what we said. Its R group has a positive charge at physiological pH. So lysine, you're supposed to remember, he's a basic amino acid, and his R group typically has a positive charge at physiological pH. Cool. So again, now we've got the 2 to 9 range. Now we're going to cross the 9 to 10 region. Maybe go to 11 or something, because I don't want to go to 11 yet. So we'll cross the 9 to 10 region. So in crossing the 9 to 10 region, the next guy to change is the amino terminus. Actually, that's going to be not enough room here. All right, so now that I've crossed 9 or 9.5 or 10 or whatever lysine's amino terminus really is, we'd now hit this predominant form. Notice how far would the pH have to go past that now to get the final group to switch its predominant form to base form? 10.53. And so once we get higher than 10.53, that's where we're at. Cool. I don't really know what to call this range because the whole 9 to 10 thing, and we have a lot of things changing in a short period of time, but it's somewhere in there. If we knew the amino group's exact pKa, we could give you an exact range. So, but that's how this thing changes. Now, when you have multiple pKas here, more than 2, I should say, finding the pi is not such a simple thing. You don't just take the average of all 3. It doesn't work that way. So what you need to do is find out where does this thing have 0 charge. And so in this case, where does this thing have 0 charge? So this one right here. And so in this case, you know what, we're going to have to get a more specific pKa for this. So the pKa of lysine amino group, I'm just going to take a wild stab and say his pKa, instead of saying 9.5, we're just going to pick a nice even 9.5 instead of saying 9 to 10. So I'm going to give a concrete value on that. And that way, so I can say this went till 9.5. This one range goes from 9.5 to 10.53. And then that's pH greater than 10.53. This is important for the purpose of calculating PI. So again, if you needed these kind of values, they would be provided for you on the exam. Ahmed.
The table you had here, is that like the pKa of the amine?
Correct. The table you've got right now is just pKas of R groups. And so in this case, that's pKa of the R groups amine, not the alpha amino part there. Cool. Sweet. So this is the form that has an overall, the prominent form where the overall charge is 0. It's his range, the boundaries of his range, that you'll take the average of to get the PI. Sweet. So what would the PI be in this case? .015 or something like that if you really work it out. That would be our PI in this case. That is a lot of work to get a PI, isn't it? Sweet. Now let's make this a little easier. Let's make this a little easier. We talked before about a charge pattern. A charge pattern. For the amine groups, the charge pattern was that the acid form has what charge? Plus, and the conjugate base form has neutral. For the carboxylic acids, the acid form has neutral, and the conjugate base is negative. When you have 3 pKas, find the 2 pKas with the same charge pattern. Acids plus, base is neutral, or acids neutral, base is negative. Find the 2 groups that have the same charge pattern. It's their average you're going to take. So in this case, which 2 groups had the same charge pattern? If we just look at our original most acidic structure, the 2 amine groups have the same charge pattern. They're positive in the acid, neutral in the conjugate base, whereas our carboxylic acid's neutral in the acid and was negative in the conjugate base. The 2 with the same charge pattern are the ones you take the average of. That's the way it works every time. Now here's the deal. Because most of the time for your amino acids, the 2 that have the similar charge pattern also have the similar pKas. And so sometimes you'll hear, oh, if you have 3 pKas, take the 2 that are close together and just take their average. Don't do that every time. That works every time except for 1. So, and if you try that exact same method on tyrosine, you're screwed. So, but the way that works every time is if you look at your 3 pKas on the charged amino, or on the acidic R group amino acids, if you look at those, all 3 pKas, find the 2 with the same charge pattern, and you're good to go. Now, if you look at the pKa listings I gave you, so for the R groups in that little table on your handout, it shows aspartic acid, 3.86, glutamic acid, cysteine, tyrosine, lysine, arginine, histidine. Here's the deal. At the bottom of the table, lysine, arginine, and histidine. Lysine, arginine, histidine, they're all amines. And what charge pattern? And they're funky amines, arginine and histidine anyways, but they're amines. And what charge pattern do amines have? Yeah, acids plus, base is neutral. Sweet. So for those, you'd take the average of them, the R group, and the amino terminus, because they'd have the same charge pattern. But if you look at aspartic acid, glutamic acid, cysteine, tyrosine, all of those, aspartic acid, glutamic acid are carboxylic acids. Cysteine is an SH. Tyrosine is an alcohol, it's a phenol. So, but all 4 of those follow the same charge pattern as a carboxylic acid, where they're neutral in the acid form, negative in the conjugate base form, and those would be the 2 pKas you take the average of for them. Now you can draw this out every time, so, but if you can remember just, which 2 to take the average of, it might shorten your time up a little bit. One thing to note, so I didn't see anything like this for you guys in everything you did. So I don't think you're really responsible for this, but if I put a peptide together, and in some major, biochem classes, we'll put 5 amino acids in a row in a string, all connected by peptide bonds. So, and when we do that, so the ones that have an amide linkage, their carboxy and amino parts have been joined together, and no longer have a pKa anymore. That was relevant because they're now part of an amide, which is not acidic or basic. But the ends, the amino terminus at the very end amino acid, and the carboxy terminus at the other end amino acid, they still have pKas that can, acidic groups and basic groups that can change based on the pKa. And so it's only the ends that you have to worry about the termini, the amino terminus, the carboxy terminus. And you have to worry about all of the potential R groups. And that's all you worry about for a peptide. Unfortunately, the bad part is you'd have to approach it just like this, where you start raising the pH, and you find out what pH you had to cross till it turned 0 overall charge, and then where that range ended, and that's where you take the average. And there's no real easy shortcut for that. So, but I didn't say anything like that in your notes, homework, or anything. So just FYI, word of the wise.
For the non-polars, we don't have to worry about them.
When you say not worry about them?
So you still have to worry about their pKas.
Well, for the nonpolar ones, if they're in the middle of the protein, do their R groups have a pK? Not for the nonpolar ones. So it's only only the 7 on that chart that are listed there that have an R group pKa. Those are the only ones you'd have to worry about in the middle of the protein. And then you'd have to worry about the amino terminus's amino group and the carboxy terminus's carboxy group. But all the amino and carboxy groups that are in the peptide bonds in the middle of the chain, they're all tied up as amides. They don't have a pKa anymore at that point. Welcome.